Hello, friends, and welcome to Global Hack Week Security Machine Learning Track Part 2. I am sure glad to have you here. Oh my goodness, Polar Void, good to see you, dude. I'm Fawad, good to see you again. Tokyo Mango, I feel like you may have been at the last session. If so, good to see you. Oh, Skycloud, I remember you were at the last session. I remember putting your name in a list. I remember that. Oh, I definitely remember Thomas was there. I think Trish Atomy may have been? Trish Atomy? I don't know. Oh, Polar Void missed the Kalimba intro because of the ad. Well, no worries. I will play a Kalimba outro if you ask me to. Oh. Cookie Monster, good to see you again. Good to see you. Okay, so friends, welcome, welcome. I guess I will do my formal intro. Hi, my name is Will. I'm a coach at Major League Hacking. I'm also a software engineer at Google, where I do a lot of cloud and machine learning things. And importantly, I'm here with you to learn about machine learning and detecting fraud, which is very, very exciting. This is part 2 of a 3-part series. So we did one yesterday, today, and tomorrow. I will say, if you have never used Python, and you are watching this and you didn't watch part 1, I would recommend you go back and watch part 1 first. This stream will be waiting for you when you finish it. I think everything will just make a lot more sense. But if you either watched part 1 or you haven't watched part 1, but you do know about Python, then welcome. You're here, and this is where you should be. Time to do credit card fraud with Will. Yes, yeah, we love making crime jokes here at Global Hack Week. It seems to be the thing. We were gonna do, what was it, IP fraud with the Microsoft logo a couple ones back, but it's a good time. So in just a few minutes, we will actually get started, and we will do a little bit of a recap of what we touched on yesterday. We will check in with our leaderboard, which we have some cool submissions, and then I am going to cause some drama. I am changing things up because it's fun and chaotic, and because I think the way things were set up earlier was not right. So there you have it. Trisha wasn't there yesterday. But you did watch it. Incredible. Well, I'm glad to hear that even though you didn't see it live, that watching it was enough to make you want to come and watch this one live. So I'm so glad that you are here, Trisha. Alrighty. So I guess first of all, I will ask if anybody has any questions while I queue up the right little screen, and I will also drop this link, which is your link to check in, which is great. You should do it. Okay, Kaka Prague, I believe I remember you from last time, and Samrid, of course, always good to have you here. Yes, Polar Void, you did hear there was going to be some drama. Okay, so this is actually, I guess this will be good. This will require a little bit of a recap. So we are doing all of our fun this week on Kaggle. So I'll drop the link to Kaggle. Kaggle is a platform where people run machine learning competitions. So I build an AI and you build an AI, and our AIs compete. It's all very, very fun. And so that is the platform we're using to both write our code and to see how well our machine learning models are doing. So I'm going to pop over there, and you can follow me. Oh, that's not what I wanted. Let's make that window small. Okay, maybe that's better. You know what? Apologies, I'm just juggling 70 million windows. Usually before a stream, I just get ready, I get in the zone, and I close all my windows. And today was not one of those days because I was too busy changing everything on the fly. Also, this is actually, we don't really do a lot of life updates, or we haven't done life updates here. I adopted a dog, which is pretty exciting. It feels like there's a pretty high percentage of people who have hung out with me on past streams. So I have a dog now. His name is Darwin. And I am going to hold up Darwin so that you can say hi. He doesn't love being held, but he does like people. All right, bud. You ready for just a little? Say hello to the internet, Darwin. Say hello. Aw, there's Darwin. And we will set him back down. Now that he's traumatized. Yes, everyone say Darwin. Darwin the darling. Love that. Yes. Cool. Yeah. I thought you might get a kick out of that. Okay, so now we'll actually get down to business, because that's what we're here to do. Business. Boom. The business of business is business. That's what I think Milton Friedman said. I can't comment on that. I'm not a business major. Yes, Starwin, getting all of the love. Love that. Well, I'm glad y'all like Darwin. I'm sure he likes y'all. Okay, so we will punch in. This is all small again here. Let's crank this up a few notches. So this is what Kaggle looks like. I think most folks were here for the last session, so I will not. I won't spend too long on here. But the two things we'll look in on are our leaderboard, which notably our leaderboard is about to get shaken up. So just get excited for that. And this is keeping track of everybody who's submitted, sort of how well they've done. So we have a lot of folks. We have a couple zeros. A lot of folks around the 13 range, and then a couple of folks up at 15 and 16. But hopefully today, actually, I know today we're going to give you tools to do even better than that for a couple of reasons. So what I want to start with is our score. So if you click on code, you can see all of our code here. And oh my goodness, we have a code submission. This is incredible. Oh, I love this. Okay, I'm going to take a look at this later, but I'm very, very excited that Kakaprog did a little notebook. So right now, if nobody else submits any other code, you just win, which is pretty cool. So if you come over to evaluation, it says that we are using an F score. And it says that we're using an F1 score. And we're going to walk through what that means and if that is actually true. So I want to jump into, this is something that I have not published, but will publish later. So this is part 2.5, where we're going to talk about metrics for a second. So the whole idea of this competition is we have some data and we're trying to make predictions about whether or not a transaction is fraudulent, right? Oh, yes. Okay. Nalara Press. This is actually a great question. How come I had over 90% on accuracy, but not a good submission score? True positive, maybe. Yes. So you are on the right track, and that is exactly what we're going to talk about right here today. Samrid said, "This is the first time in a while Will hasn't promised to paint his hair or face or something." LOL. Yeah. Okay. So I like if you have not done previous Global Hackers with me, oftentimes I will have some silly competition that's like, oh yeah, like every time you attend a stream, cast a vote for what color I dye my hair. The thing is, I can't do those all the time. We're now doing Global Hack Week every month, and it's like, oh, I don't have enough parts of my body to mutilate for you. But soon we'll do another one of those. Okay, so let's get into it. So the title of this one is Understanding Precision, Recall, and F1 Score. So we are, let's come up here. So we want to make that code or markdown. We are in the business of making predictions, right? So we have some data about a transaction, and we're trying to predict, is this fraud or not fraud, right? And there are a couple of ways that we can measure how good our predictions are. So Nalarepas mentioned they were getting really high accuracy. They also mentioned this thing called true positive. So we're going to look at a whole lot of metrics. And for the example, I wanted a really, really simple example. So I have this very simple data frame. We're going to import some random metrics to look at later. But I created this very simple data frame for cancer predictions. So say we have 4 patients, and 2 of them have cancer and 2 of them don't have cancer. And we're trying to predict which ones have cancer. So 0 means this guy doesn't have cancer, 0 means this other person doesn't have cancer, and then the 1s mean these 2 poor souls do have cancer. So we could imagine if we made perfect predictions, our perfect predictions would look something like this. And maybe here, I'll just render this. We can say df head. If you weren't here last time, a data frame here is kind of like a spreadsheet in Python. It just lets us kind of mess with our data in a really easy way. So has cancer, the first 2 are false, and the last 2 are true. So our perfect predictions would look exactly like the truth, right? And that's obviously always the goal. That's what we want to do. But there are 2 different ways we can make mistakes. And one of them is called a false positive, and the other one is called a false negative. You have probably heard of these before. So what if, instead of perfect predictions, like we have in this second column, in our third column, we do 1 false negative. So one person who has cancer, we actually say they don't have cancer. One note that I'll throw out here is that when we talk about false positives and false negatives, sometimes it's obvious, but sometimes it's like, well, what's a positive, what's a negative, right? In this case, having cancer is the quote unquote positive result, because like that's kind of the important one that you would go and scream about, right? And in fraud, fraud is kind of our positive case, right? So if fraud has been conducted, that means you gotta scramble the jets and you gotta do something, right? A negative finding is basically, whatever, right? Nothing happens. So a false negative means there's someone who did have cancer, they were a positive, but we falsely called them a negative. So patient 2 right here, they really did have cancer, but we said they didn't. And then this last set of predictions it's an error in kind of a different way. So this last one, instead of a false negative, we have one false positive. So patient 0 didn't have cancer, but we predicted that they did. We put a 1 in their row. So before we get any further, does this whole business about false negatives and false positives make sense? A false negative is someone who did have cancer. We told them they didn't. And a false positive is someone who is healthy. We told them, oops, you got cancer, right? And those are both problems. But think about which problem is worse. I want you to, in your head, actually, in chat, why don't you tell me, what's worse? In this case, is a false negative worse, or is a false positive worse? So false negative is telling someone who has cancer that they don't, and a false negative is telling someone who has cancer they don't, and a false negative is telling someone who doesn't have cancer that they do. Okay, yeah, we have a couple of answers here. Oh, okay, there we go. Oh, y'all are great. Y'all are a good crew. I like this Mobile Hack Week. Yes, so we got a ton of correct answers. A false negative is worse, right? If you don't have cancer and I tell you have cancer, okay, you probably freak out, right? But you go and you get additional tests and you realize you don't actually have cancer, and ultimately you're fine. If you're a false negative, then that means you actually do have cancer, and I just told you you're healthy, right? If I tell you you're healthy, you're just going to go off and not do anything else, and you'll go live your life. And then, a year later, you realize you have serious complications because your cancer wasn't diagnosed correctly. So this idea of false positives and false negatives not really being symmetrical, this becomes really important for us. So without further ado, we're going to talk about 3 things: precision, recall, and F-score. I guess actually first we should mention accuracy. So accuracy is kind of the easiest one. It's like, how many of them did you get right? And we can just calculate the accuracy easily, right? So in our perfect predictions, our accuracy is 100%, right? There are 4 questions and we get them all right? Easy. What's our accuracy for this row called 1 false negative? Well, you can see how many do we get right? We get 3 right, and then this patient 2 we get wrong. So that's 3 out of 4, that's 75%. Okay, 75% accuracy. And then 1 false positive is exactly the same. We get a different thing wrong, but the accuracy is still 75%, right? So if we look at our rows of predictions, our first set of predictions, the perfect predictions, get 100% accuracy, and then the last 2 both get 75% accuracy. But we don't really care about accuracy that much, and we'll kind of understand why in a second. So first of all, I guess actually really the reason we don't care about accuracy is because our data set right now is imbalanced, right? If you look at the data set, you'll see that like 91% of the transactions aren't fraud. And this makes sense, right? Because like most transactions aren't fraudulent. Most transactions are fine. But that means that you can easily get 91% accuracy just by saying everything is fine, right? And that model is not actually useful to anybody. But you still get 91% accuracy, right? So we're looking for a metric that tells us more than just what percentage of these did you get right. So what is precision? The classic definition of precision is your true positives divided by your true positives plus your false positives. So essentially, a true positive is someone who, in this case, someone who has cancer that you tell them they have cancer. And a false positive is someone that you that you say you have cancer, but they don't actually have cancer, right? So precision is essentially this measure of all the stuff you said was important, how many of those things actually were important, right? Out of all the people you said have cancer, how many of them actually had cancer? And so we can check our precision for all of these. Actually, okay, I should actually clear all output because I want to do a little quiz. Let's see. Can I clear all outputs? Boom. Okay. So right now, we are getting the precision of our perfect predictions. So whether or not you have cancer goes first, and then your predictions about that go second. So what will our precision be if we have perfect predictions? If we're exactly correct all the time, what's our precision? You could guess in the chat, or you could just log it in your head. Polar Void says one question mark, and yes, that's exactly right. In general, if you're absolutely perfect, basically all of these will be 1 or 100%. Yeah, Trisha also correct. Great. So what is our precision now if we have one false negative? So remember, our precision is defined as true positives divided by true positives and false positives. So if we have one false negative in our predictions, what does that do to our precision? It's still 1, right? Because out of all the people that we said have cancer, all of them still have cancer. We said fewer people had cancer, and we left a couple people out, but still, out of all the people that we said have cancer, all of them still have cancer, right? So we were very precise, right? And then finally, what if we have one false positive? So remember, our true positives divided by true positives plus false positives. So out of all of the people that we said have cancer, how many of them really did? And if we have a false positive, suddenly we have become less precise, right? Suddenly we drop down to 0.6666, or this is 2/3. Because remember, we said that 3 people have cancer, and only 2 out of the 3 people really had cancer. So this is precision. Yes, Polar Void, correct again. Okay, do we have any questions about precision? Yeah, this is just all 6s, my guy. Yes, Polar Void and Trisha on top of it. Look at that. 2/3. Boom. Any questions about precision? The thing to think about is, of all the people we said had cancer, how many of them really had cancer, right? And you can imagine caring about this because, you don't want to tell a bunch of people that have cancer when they don't. That's kind of what precision tells you. Okay, so now what is recall? Recall, kind of similarly, is defined as true positives divided by your true positive plus false negatives. Now, all this terminology I know can get a little bit liquid in my brain sometimes. But the way to remember this is it's the stuff that actually was important. Of all the things that actually were important, how many of those did we say were important? So of all of the people who actually have cancer, how many of them did we tell, right? So if 100 people had cancer and we only told 50 of them, then our recall would only be 50%, right? We only actually told half of the people with cancer that they had cancer. And so recall actually ignores all the people that don't actually have cancer. We don't care about them. They're fine either way, right? So if you want to have a really, really high recall, you would want to tell lots of people they have cancer, right? You'd want to err on the side of just telling people they have cancer. So if we do our recall score on our perfect predictions, you should be able to guess that we still get a 1, right? Because it's perfect. There are no errors. For our recall with one false negative, we get 0.5, right? Because now of all, there was one person that had cancer that we didn't tell. And so half of all the people with cancer went home empty-handed, right? So that actually really damages our recall score. And then what if we have one false positive? We're actually still at 1, right? Because recall doesn't care if you're a little bit liberal with telling people they have cancer, right? It doesn't actually matter that much because those people will be fine. That's sort of what recall says. I want to before moving on, I want to throw it out to y'all. Do y'all see any issues with precision and recall as metrics? If I just told you, hey, we're just gonna grade this based on precision, or we're just gonna grade this based on recall, do you have any thoughts as to why that would be a bad idea? I really should have some Jeopardy music. Yeah, so Polar Void says they don't show us the whole picture, which is right. Definitely each of these, they sort of only focus on one aspect. But part of what this means is that they're really easy to game, right? If you want to get 100% recall, that's easy. Just tell everybody they have cancer, right? Or if you want to get 100% precision, just tell everybody they're fine, right? This is kind of what we saw in our, similar with accuracy, this is what we saw in our imbalanced data set when, when 91% of transactions are fine, it's like, oh yeah, just say all of the transactions are fine and you get 100% precision, right? You never raise a false alarm. So we need something better than that, right? And so for this competition, we've been using F-score. So precision and recall both have their limits. They can each kind of be gamed one way or the other, and F-score tries to balance them. So technically, the equation for F-score is 2 times the precision times the recall divided by precision and recall, or precision plus recall. So this is sort of a way of, it's not really an average, but it kind of, it kind of combines them in a way that you have to do pretty okay on precision and pretty okay on recall as well. What we can do is we can look at our perfect predictions, which again should be perfect. We get a 1. But now we can check our, let's see, 1 false positive. And we get 0.66 again. And then we could do, that was 1 false negative, and then 1 false, oh wait. Yeah, okay, yeah. And then 1 false negative. And we need to include beta. And we get 0.8. So this is hopefully a little bit of a softer, like it takes both of them into account, and neither of these are too easy to game. Polar Void asked, what's the beta for? And great question. So beta basically tells you how to weight things. If beta gets higher, you care more about recall. And if beta gets lower, you care more about precision. So the way that we can see this is if we increase beta, so what if we increase beta to 2? Obviously our perfect scores stay perfect, right? But if we increase beta to 2, our false negative gets actually worse. So we're punished for having someone who did have cancer and not telling them, right? But if we have a false positive, originally it was 0.8, and if we increase our beta, the false positive gets actually better. We now actually get a higher score for our false positive with a beta of 2. So we're sort of, as beta gets higher, it's kind of telling you, hey, tell more people they have cancer, right? That's kind of what they're suggesting to you. And you can, of course, go in the other direction, and you can say, okay, what if beta is 0.5, right? Of course, if our predictions are perfect, we still look perfect. But in this case, our false negative actually gets better, right? So we're kind of being more forgiving of our false negative here. And our false positive actually gets worse. So this is really saying, hey, we don't want to cause alarm. We don't want to freak too many people out. Be more precise. Don't be as focused on recall. Let's see. Moshin asked, where did you get your data from? So I will say, if you're looking at the whole Kaggle competition, I can actually talk about that a little bit later. If you're looking at the whole experiment or the whole competition, we can look at that later. This cancer data, it's not even real data. Actually, it is. If you just scroll up here, I just made up a few numbers just to have some stuff to play around with. But good question. Yeah. So Fouad asked, how is beta decided? And this is where I caused some drama. Okay. So originally beta was equal to 1 for this competition, and that basically means balance, precision, and recall equally. Right? But something happens when you're balancing precision and recall equally and your data set is still really, really imbalanced. It can have funny effects where it's actually advantageous to tell 90% of people that their transaction was fraudulent, right? And I didn't like this, and I also felt like it made the competition kind of hard. So what I did is I actually changed the value of beta used to be 1, and now the value of beta is 0.5. So that is a value that I have picked, And it hopefully strikes this balance of, yeah, you want to tell people whose transactions were fraudulent that they were fraudulent, but don't just go around telling everybody it's fraud, it's fraud, it's fraud, because at some point that gets annoying and people kind of become inured to what you're saying. So this is our little deep dive into precision recall and F score. Really, not F1, it's really F score, because right now it's F.5 score. And I will publish this. Actually, I think I'm going to add, to make this part of the competition, I will add, never mind. Maybe I'll connect to the competition later, but I'll make it public. Save. Boom. Good deal. Let's see. F1 is F score with beta equals 1. Yes, this is a great point. This is actually something that I only actually learned last week, because I was like, wait, why do I see F beta everywhere? And I'm just looking for F1 score. And yes, F1 score is just F beta when beta is equal to 1. Polar Void asked, we need to get you more upvotes. Yeah, go upvote things. Go participate. Actually, okay, this is a great moment to talk about all the ways that people can win swag drops in this competition. So I am offering 5 ways for you to get swag dropped. And those ways are, first of all, on our leaderboard, boom. On our leaderboard, if you are first place or second place, you will get a swag drop. Just like no questions asked, you got first place or second place, good on you, you get a swag drop. The next 3 are for sort of other things you can do. One is actually for the best notebook. So currently, Kakaprog is the only person who has published a notebook, and so they are winning this by default unless anybody else submits a notebook. My notebooks, of course, don't count. Then we are also giving out a prize for the best conversation. So this can either be a comment on a notebook. So for example, if you had a question about this data analysis, you could come over here and leave a comment. You could type out your comment and post comment. Or you can start your own discussion under the discussion tab. Currently, I posted one, but that also does not count. As a kind of separate thing, I don't think we've talked about the Kaggle progression system, but maybe I'll pull that out. So the Kaggle progression system, boom, is a way of, I guess there are 5 tiers that you can be at. And so everybody by default starts as a novice. And to become a contributor and to level up, you have to do 4 things. You have to make a notebook or script, which I believe that just by copying one of mine, that counts. You need to make 1 competition submission, which everybody who's submitted has already gotten this one. You need to leave 1 comment on something, and you need to give 1 upvote. So all of you today, if you wanted to, could become contributors. And then after that, you have to go and start doing more stuff on Kaggle. But if you wanted, you could become a Kaggle contributor and get a cuter icon for yourself. Will it give you extra points if you add memes? Yeah, absolutely. If you add memes to your notebook or your comment, that would be worth a lot to me in my book. Good deal. So if we don't have any other questions, maybe we get started on actually learning more things. Oh, could I share a link to it? Yes, I will share a link to, let's see, share, copy link. Boom. So there is the link to what we were just looking at, understanding precision recall and F-score. So now we know actually how we're getting graded, right? You both care about precision and recall because they get blended together in this score that is your F-score. And because I changed the value from 1 to 0.5, it actually should get easier. So if you resubmit the same your same submission, you will probably get a higher score. Yes, lots of swag drops all around. Boom. Okay, cool. Maybe we'll call it on that. And we will enter, oh, not part 4. No, part 3. Yeah, I still need to publish part 4. Okay, part 3. So last time we did some, and I guess maybe a good moment to actually just poke out. We did a Python crash course where we learned about Python. We did a lot of basics there, and importantly, we learned how to use pandas. And then we also did some exploratory data analysis and found out how to submit, right? So in our exploratory data analysis, we looked at univariate analysis. So we looked at just one variable at a time to see kind of where things fell. And then we also looked at bivariate analysis and looking at how things correlate. And so one of the things we noticed was that the distance from home correlates with fraud. So one thing we said is, hey, like maybe if you are really far from home, maybe we just call that fraud, right? And so we built a model that basically said, if you are greater than 10 miles from home, we're just going to say that that's fraudulent and just dust off our hands, right? And obviously this was not, it's not a perfect model. It's not even a really good model, but it does, it did something, right? It got us some predictions. And I believe, yeah, so our accuracy was 64%, right? And then when we submitted it, originally, I believe we got, I want to say like a 13 F score. But if we come in and we submit it again, I would expect us to get a higher score. Actually, it might be lower. You could go and try. But we did some exploratory data analysis. And our model was really dumb. But so now we really want to power up our model with some actual machine learning. And that's what we're going to do today. So if you come over here, you can click Edit. And yours will say, like, I think copy and edit. And so you can get your own copy of this code. Polaroid said, how would our equation change with a different beta value? Yeah, so this is a great question, Polaroid. So as beta goes up, you favor recall. So if beta gets really, really high, you can do better by telling more people it's fraud, or you can tell more people they have cancer. But as beta gets really low, that means you have to start being more precise to do well. So you have to move away from telling everybody it's fraud or telling everybody they have cancer. So one thing that you can imagine in an imbalanced data set, if most of your cases are negative, a lower score, a lower beta, will help you get a higher score. That's like kind of a hand wavy explanation, but that essentially. You're actually asking how the. I'm sorry. You're actually asking how the literal math works, and I believe here we can just look up equation for F beta score. You have beta in. This is not a great. Maybe this one. Okay, yeah. So here you're introducing beta as this multiplier on precision. So as your precision goes up, your value here actually gets lower. And so this has the effect of the higher beta is, the less precision matters, if that makes sense. Hopefully that makes sense. Good deal. Samrid, I have to go to uni. Oh, okay. Well, I am glad that you were here. It was nice to see you, and good luck at uni, friend. Okay. Building a basic model and submitting. Great. So we are familiar with pandas now, and it makes sense for Polaroid. It's one of those things that's like, I understand F beta scores for like 5 minutes at a time, and then I kind of forget about them, So we import pandas and we import our training data set. You can always see your data over here. So this is the data that I am giving y'all, and the training data set has all our labels. It has your distance from home, your distance from the last transaction, the ratio to median purchase price, whether or not this is a retailer you've shopped at before. So it's a 1 if you've visited them before, whether or not you used a chip or a PIN, or if it was online, and then finally if it was fraud or not. So this is basically all the stuff we did yesterday, just getting it in there. So we built our kind of our own sort of dumb model from hand where we picked a threshold, right? But what if we could have a computer pick that threshold for us? And better yet, what if it could consider all of the columns, not just one column? This is kind of what a logistic regression model does. So logistic regression, it picks a weight for each input variable and then multiplies all the input variables together with their weights, adds them together, and compares that to a threshold. This is a great model to use for classification if you think that the relationships in your data are linear. In this notebook, there's a little link to dive deeper into logistic regression. But it's kind of like what we were doing earlier, where you have a threshold, but instead of just looking at one variable, if it crosses the threshold, you combine all your variables together. And because we have this training data, our computer can just figure out what the right thresholds are for us. So there's a library called sklearn, and honestly, I will take this chance to plug sklearn. It has incredible documentation. So if you just go look up sklearn documentation. Oh, hey, they have F beta score and precision score. What if we just looked for logistic regression, linear models, logistic regression? This is probably kind of small. One of the things that I love about this documentation is that it tells you all about the thing, but it also shows you an example of how to use it. So actually, I will just come back here and I will Google linear or logistic regression. Can I spell logistic regression classifier? Boom. So here's a page of documentation on the model that we're about to use. But if you scroll down, boom, it just has a snippet of code that just tells you exactly how it works. And I think often just finding an example of the code is sort of more useful than like just seeing the pure documentation on it. So big plug for the sklearn, or scikit-learn is what it's called. So we can import this logistic regression model and just create the model. But right now the model doesn't know anything. So we've created our model, but it doesn't know anything. Now we will grab our input columns. So if you scroll back up, our first column is ID and our last column is fraud. And neither of those we actually want in our training data. So we can grab just the ones in between there using a slice. And so our input columns, if we run this, we see we have distance from home all the way through the column, whether or not it's an online order. And so those are all of the things that we actually know when we're going in to make a prediction, right? So once we have our input columns, we just call this function called fit. So fit is where our model actually does the learning. This is the learning in machine learning, right? You put in your input columns, and then you also put in what you're trying to predict. And so now the sort of the genius of this model is that it is going to go and figure out what sort of parameters it can have, or sort of how it can turn the dials to make the best predictions for you. And this is sort of the beauty of machine learning is you don't have to tell it really how to do this. It's going to figure it out on its own. We could talk more about if you want to go sort of more into the theory on what does the math look like behind this. I'm more than happy to dive a little bit into that, but don't want to get too deep. This is a really simple model that just sort of adds your variables together and see if they're greater than a threshold. So now we can score our model. And so if you remember, this is the problem is, oh yeah, our model will probably just tell us that everything is fine because it can get 91% accuracy just by saying everything is fine. Okay, Cockerfrog asks, can I select only the columns that have a correlation? Yeah, so this is, there's this idea called feature engineering that's sort of, feature selection and feature engineering, and it's sort of picking what do you give to your model. And this is totally a thing that I would recommend trying things out on. So yeah, you can definitely remove some of your columns if you think they're not useful. And you can also like combine columns or create transformations of columns, right? So maybe one of your columns could be the square root of distance from house, right? That's like another column you could put in there. So yeah, you definitely that's definitely something in bounds that you can play around with. So our accuracy was really high after we trained our model. But what are our actual predictions? So now that we have a model, so model score just does the accuracy by default. Model.predict actually generates predictions for us. And so if we run model.predict on our input data, and we look at our predictions, you can see they're just all 0, right? I mean, we can even take the mean of it to see, on average, what are you predicting? But like literally, we're producing just zeros in our predictions. And this is, of course, a problem, right? Like we know the best way to get high accuracy is just to say, yep, it's all fraud, right? And this is not particularly helpful for us. So what do we do? This is, of course, so we already kind of talked about F-score and recall and precision. And so this is something that we're going to have to deal with. So one thing that we can, I guess we should just calculate what our F score is, which this is now no longer F score. It's just now no longer F1 score. It's just F score. But we can import our F score, and we can make our predictions. And F1 score here just tells us what our score is. Oh wait, we don't have F1. F beta. Boom. It's like your Oprah, but you accuse people of fraud. Yes, you get a fraud. You committed fraud. Darwin definitely committed fraud. That is good. I am like the Oprah of telling people they have done fraud. And so yes, of course, you could probably guess that our F score is going to be 0 because our recall is literally 0, right? And if you multiply anything by 0, it's 0. Now we have great precision, right? We have our precision is technically 1, right? In fact, we could check this if we wanted to, if we did precision score. So if instead of F score, we just look at our precision, it should be 1. Oh, that's not right. What? Our recall certainly isn't 1. Oh, recall. Oh, I guess technically precision is still 1 because we don't have any positive cases. You need at least one positive case for your precision to end up like being a valid number. I think it's defaulting to 0 here. But so our F score is 0, and that's a problem. So there are lots of ways that we can try to deal with this. But one way that we can do it is to tell our model that we want it to care about our data classes equally, right? By default, your model is going to try to minimize the number of times it's wrong. And so it's going to overweight classes that are overrepresented, right? This is a thing that we hear about all the time in like facial recognition. And if it was trained mostly on faces of white people, it will not do that well on faces of black and brown people, right? This is a case where the model is sort of weighting towards what it saw in its training data set. And in this case, our model saw a lot of cases of it's fine in the training data set, and so it weighted those more heavily. But one thing we could do is we could just explicitly tell our model, hey, care about these classes exactly equally. And a pretty easy way to do that, which, okay, I should clear outputs again because this is ruining all the drama. Boom, okay. So we can create logistic regression, our logistic regression model again, but we can say our class weight is balanced. As this is basically saying, hey, whatever imbalance there is in our data set, just shift it so that you care about all of the classes equally. You care about predicting fraud right, and you care about predicting not fraud right. And if we run this, you will see we actually get, not 42% accuracy, we get 47% accuracy, which is interesting. That's like actually kind of a lot worse, right? And this makes sense because we're actually telling it like, yeah, you don't need to care about saying not fraud that much, but there's a lot of not fraud in our data set. So we are actually making accuracy worse, but let's take a look at our F score, not F1. And we end up getting 27. And if you remember from last time, I believe that it was like 0.13 or something. So our F score has actually increased drastically. Also, you should notice that that 0.27 is, if we go back to our leaderboard, that is higher than the current high score on the leaderboard. So we sacrificed a lot of accuracy to get a better F score. But something that I would actually like to just check now is of our predictions, what percentage of them, we can just say .mean, what percentage of them do we say are fraud? Okay, so right now we are saying our model is saying 53% of things are fraud, right? And obviously that's like that's pretty bad, right? That's still pretty bad. It's maybe not as bad as telling everybody literally or telling nobody ever that it's fraud, right? It's probably better than that, but it's still not good. This is like you swipe a credit card, half the time you get a notification saying, we think you just did a crime. That's not a great user experience, but still better than before. So if we wanted to, we could basically use those predictions as, or use that model to make predictions, right? So why don't we load up our test set, So we can, similarly to grabbing our train set, we can just grab our test set file right here. And you'll remember from last time that our test set has all the same kinds of data, except it's not labeled. So this is some additional transactions that weren't in the training set, but there's no label telling you if they're fraud or not. And you have to produce the label of whether or not this is fraud. So we can use our same balanced model, take our input columns, and make predictions. And so you can see, okay, a lot of these are sort of positive, yes, it's fraud predictions. We can check what percentage of them. Yeah, okay, again, 53% of these are being classified as fraud. And now we can put those, so I'll walk through this line by line, but we're copying our test data frame into a submissions data frame. So this is the one that we'll actually use to submit. We're going to add our predictions as a new column called fraud. So we're pushing in our predictions into the fraud column. And then we're just grabbing the ID and fraud columns and pooping them out into a submission file. And so you can actually come over here to our output directory, and you can see there's now a submission file in here, which I feel like usually you could download it to check it. I guess it's not going to load for us. And if we just look at that, it looks like, okay, yeah, we have our ID and we have whether or not it's fraud. Before you submit, it's always a good idea to look at the sample submission and just make sure it looks the same. And you can look at the sample submission, and yeah, it basically looks the same as our submission. You have ID in one column and fraud in the other one, and these IDs are the same, right? It starts with 1, 2, 3, 6, 7, and this one starts with 1, 2, 3, 6, 7. So it looks good, and so we can submit this. So if you've been following along at this point, you should be able to hit submit. And hopefully some people were following along, and we can, in real time, see how the leaderboard changes. I think this is going to be probably a shorter stream. We are going to, after we see how we scored here, I think we're going to look at one more kind of model. And then, okay, our submission is complete. Let's see how we did. I guess we'll go over to the leaderboard. Oh no, it's worse. What? 0.0976. That's unfortunate. Yeah. Well, okay, this is actually a good thing to learn about the dangers of generalization, right? It looks like our score that we calculated was not as good as the score that we got sort of out in the wild. And we'll have to learn why that is. I will also have to separately just make sure that I didn't do anything crazy. So give me just 2 seconds. I say 2 seconds, but I don't actually mean 2 seconds. I really mean several seconds. I'm going to go into the back end here and just make sure. Okay, yeah, our beta value is 0.5. Okay, cool. So I don't think we're going to worry about that. I think that's just dandy. I think that's fine. And I think we'll hop to another notebook. So let's look at, actually, yeah, this is great. This is a classic problem that we face, overfitting. I am going to pop in part 4, which is not published yet, but I can publish it. I guess I'll publish it now. Why don't I? As long as it looks like everything. Yeah. Okay. Cool. We can do it live. Boom. Public. Save. Share. Yeah, that was unexpected. You see, this is I caused drama, and I caused drama for myself as well, right? I was changing it. I was like, oh, this will be cool. This will be a fun time. And then boom, 0.09. So I guess technically, I think our our random just like pick a number thing to. Oh, actually, okay. I think I know what's going on here, but we'll have to talk about it. Okay, so let's close that. I guess a couple things to throw out. One is if you click over here, you can see all of your active sessions. We haven't used GPUs much, but if you use a GPU, you can only use one GPU at a time, and so checking out your active events is a good idea there. The other thing I guess to touch on is if we come back here, come on. Oh my goodness, my windowing system is just being so upsetting these days. I think I need to restart Rectangle. If we look at our leaderboard, you can see, I can see this because I am in control of everything, but I have a public score and I also have a private score. And these scores are not the same. And what you see right here is the public score. And the final results are based on the other 30%. So there could be a shakeup. Someone could be first place in the public leaderboard, and they could drop down to third or fourth place. Usually those things correlate, but something to be aware of is your public leaderboard score is just an approximation of what you'll do. Will's next stream will be in the Apple Vision-y thing. Yeah, we'll give it a shot. Okay, y'all, it's so dumb, and there's that small part of my brain that kind of wants one. You know, it does look fun. It does look fun. Okay, so powering up our model. I want to look at two different things. We're going to try to dig into cross-validation and something called nonlinear models, which for us will be a decision tree. So let's see. Our linear regression model after our change to our F-score, actually, well, before the change, it was getting about 1.5. But when we submitted, we got a lower score. This, I guess, is the important thing. When we submitted, we got much worse score. I should be very vague here. And there are a lot of reasons for this. But one reason is that when you train your data on, or when you test your data on training data, it's fundamentally questions that it's already seen before, right? It kind of knows the answers deep down. So the analogy that I always throw out is that when you are using your training data to evaluate your model, it's kind of like taking a test where you have already seen all of the questions and the right answers. And so one thing that we can do to get a more realistic estimate of how well our model will do on data as it's seen before is to split our training data set up into a training set and a validation set, and then train it on part of it, and don't show it that other part of the data set until we want to actually test it to kind of know what to expect. And so that's the first thing that we can look at here. We can still pull in logistic regression, and we don't need F1 score, but we can bring in F beta. And we can grab our training data. And now from scikit-learn, we're going to import something called train test split. So train test split just splits up our data frame for us into a training set, and we'll call it a validation set. So VAL or val is our validation set, but it'll call it a train set. So we can run this, and then we can just check at how long each of our data sets are. So I think originally, what was it? We had like 1,800 rows or 18,000 rows in our data set. And so now 13,000 of them are in our training, our sort of training split. And then we have 4,500 left in our validation test DF. So that tells us that we split our data set up in that way. Do we have questions about the idea of splitting it out into a sort of validation training and then a validation testing data set? This is sort of like the idea of now instead of just showing our model the test, we are giving it a study guide, and then the test is sort of separate and secret. Wouldn't we want to set the randomized thingy to be consistent to? Sure, we could. Here, let's set our random state. Random state is 12. Boom. So setting a random state is just a nice thing that anytime there's randomness in your model, if you want it to be reproducible, you know, I want to run this and then I want to run it later and have it say the same thing, then adding your random state can be useful. Or like me, you could just change the metric you're using like 30 minutes before a stream and then see everything shake up. So all of this should be familiar again. We're grabbing the input columns, and we are telling our model that we want it to be balanced. And then we are calling model.fit on our validation training data and our validation training target. So I should do the same thing where I clear the cells. Clear all outputs. Boom. But we can rerun these. So now we can actually, instead of testing on the same data it was trained on, we can actually test it on data that it hasn't seen before. And so that was sort of the point of splitting up that initial training data. So we'll do our F beta score again and 0.24. Okay, so maybe we have a little bit more faith in this now. Maybe not actually. Maybe there's still funky things going on. Actually, there's part of me that's like what if beta is 2? Oh, is it possible that they've swapped beta? They've inverted beta? That could be tricky. Okay, y'all. I have to apologize that we are doing this live. But I think I'm going to try swapping it and see if that gets us the results that we are expecting. So let me sneak this off screen so y'all don't see my secret backend here. But I am going to really quickly, hopefully really quickly, actually shift. I can even show you. So this is where I set up the competition. I had in the beta value, I had 0.5, but I think that they might have beta inverted so that 0.5 actually means 2 and 2 actually means 0.5, which would be easy to do because in the equation you actually subtract it from 1. You probably don't actually care about this, but I'm going to pull that off screen so I can try setting it to 2. And we'll see what happens. It will take just a second for me to update. I think in other global hack weeks, I would say, oh, let me see if I can fix that afterwards. But I feel like this is a very friendly global hack week, and so we will just increase. It's both very friendly and very dramatic, right? We're just channeling the drama all week long. Okay, cool. Sample submission. Open. Almost done, y'all. I promise. If this doesn't work, I will just go off and figure out why it's being funky. And okay, I think that would work. So let's actually go back to not part 2. Let's go back to part 3 and resubmit this. So remember with part 3, we were getting an F score of like 0.275, but then our score showing up on the leaderboard was 0.097. But after I changed that parameter, I'm curious to see if that's going to flip over to the 0.27 into that range. That's what I would hope. Could we also check how many false positives and negatives each we get? Yes, we could calculate that. There might be a false positive count function in scikit-learn. Okay, let's check the leaderboard again. Okay, 0.244. There we go. Okay, this is great, actually. This is perfect. So we did just need to flip it around, but now we are getting better scores. So if you were following along and you resubmit part 3, you should jump up and get a 0.24-ish kind of score, which now I just kind of want to sit here and refresh the page and see if anyone pops up. But I won't do that because we could be here. There we go. Okay, Derek Gu. Well done, 0.3. That's a pretty good score. That's better than the score that I just got. Incredible. So, on that note, oh yeah, y'all go upvote all the notebooks, please. Yeah, on that note, let's go back to powering up our model. So we thought we were going to get 27, and we ended at or 0.27, and we ended up getting 0.24, right? And so this still kind of proves that point of the score that we got on data we hadn't seen yet was a little bit lower, right? Oh my goodness, my windows are freaking out. And so here, now that we're testing on data that we haven't specifically seen, we actually get a better estimate of what to expect. This is now telling us 0.24, and so we're not going to be surprised when we submit and we get a number closer to 0.24. So this is lower, and it's probably a more realistic estimate of what our model is going to do on new data. Do we have any questions about this idea of cross-validation and having this sort of this holdout set that we get to use? If we have any questions on that, happy to go into it. Otherwise, we can get to some exciting new models. So my hand-wavy explanation of linear regression is it kind of adds all of your variables together, and it checks to see if they're greater than a threshold, right? If they're higher than that threshold, it says, yes, that is fraud. And if it's lower than that threshold, it says, no, that is not fraud. But one of the limitations is that that means that all the relationships between our variables kind of have to be linear, right? There's not a way for this model. All it's doing is multiplication and addition. So there's no way for it to learn some sort of more complex relationship. And so like, for example, what if the ratio to median purchase price only means that it's more likely to be fraud if repeat retailer is false, which means like the card holder has never shopped there before. This is a classic sort of nonlinear relationship, right? It's like there's an if-then, and it's not just that this thing is always true, it's that it's true in some cases, right? And so this is a relationship that a linear regressor could never actually pick up. But there are other models that can learn these kinds of relationships. And one of them is a decision tree. So a decision tree is kind of like a flow chart. It says, if this, then go over here, and if that, go over here. And it keeps asking these questions until you get to an answer of, yes, I think this is fraud. No, I don't think this is fraud. And we can look at what this actually looks like. So first, we're going to import sklearn.tree decision tree classifier. And if we go and we look at the documentation, I'm sure we'll get some great stuff. We get a little example, so go check the documentation. And now we can just jump ahead and we can say class weights balanced. So we're creating a decision tree on this line. We can say class weight balanced, and then right now we're going to say max depth equals 1. So the catch here is that saying that max depth equals 1 is basically says you can only ask one question, right? If the tree can only go one layer deep, that means you have to ask one question and then you're done. And we'll play around with this. This is something we'll expand later, but it's easy to start this way. So now we can take that same validation training set and our validation training target of whether or not it's fraud, and we can fit our decision tree. So instead of learning how to add all of our variables together and compare them to a threshold, this is instead learning what would be a really good question to ask to try to figure out if it's fraud or not. So we can run that, and we can do the same scoring. Although, why don't we actually, before that, do this visualization? So what has our tree actually learned here? So we can actually import our old friend matplotlib, and we can actually visualize what our tree actually has learned. If you run this line of code, we basically have, this is our simple decision tree with depth equals 1, right? It only asks one question, and the question is the distance from home, oh wow, big, is the distance from home less than or equal to 2.904? So remember, this is actually really similar to the question that we asked, right? We asked the question, oh hey, if it's greater than 10 miles, like maybe we call it fraud, and if it's less than 10 miles, maybe we say it's not fraud. And so you can see over here, it's saying, okay, if it's less than 2.9, then maybe we say that that's not fraud. And if it's greater than 2.9, maybe we say that it is fraud. But this is still pretty simple, right? So what if we said, instead of max depth 1, what if we said max depth 2? So instead of asking only one question, we get to ask 2 questions. And so here you can see that our tree has become a little bit more complex. So it actually starts with a pretty similar question. It says, hey, is your distance from home less than or equal to 2.9? And if it's not, or if it is less than 2.9, then it comes over here and it says, okay, was your distance from your last transaction less than or equal to 13.1? And if so, then it makes a decision from there. Over here on the other side, it says, okay, if your distance was greater than 2.9, well, is it between 2.9 and 11.5? And if it was, then then it keeps going. So this is a decision tree. And one of the things that I love about decision trees is that it is really easy to understand what they're doing, right? They come up with a set of rules and they just follow them. And all you have to do is just look at that set of rules and you could be the decision tree if you wanted, right? Like this is a model that it's very easy for me to just mentally understand. And I think that when you have really complex systems, it can actually be really powerful to be able to understand what they're doing. And that is one thing that decision trees are really, really good at. Thomas asked, is it better to have as much depth as possible? Yes, so this is a great question. And the answer is up to a point. This is actually something that could be kind of fun to look at. So usually the advice that you will get is if your decision tree is too big, you can do what's called overfitting, where instead of learning these general things about the tree, it just ends up having a specific file on each training sample and doesn't actually learn anything generalizable. But we could figure out where this limit is for us, right? So for starters, let's just score. What do we get here? Okay, 0.29. Yes, Polar Void, conspiracy theory brain. So our F-score got even better with a decision tree, 0.29. But what if we copy this code? So what if we, let's grab all this code and run a little experiment. We're doing it live, y'all. So this little snippet of code here is going to, and actually, let me know if this is okay. I'm going to make this a little bit smaller just so we have a little bit more space. But if that's too small, I can make it bigger. Polar Void asks, wait, did you leave the beta at 0.5 or change it to 2? Yeah, so this is what I was saying is that at least empirically, the Kaggle implementation of F beta is different from the scikit-learn implementation of F beta, and they actually just invert it. So 0.5 in scikit-learn is the same thing as 2 in Kaggle. So that is why those things weren't lining up. But yeah, that is weird. It kind of makes sense because it's just 1 divided by the thing. But yeah, that's maybe, I don't know. Somebody should fix one of those because that's kind of confusing. Okay, so we have this is the whole process for training and scoring a decision tree, right? But what if we wanted to try lots of different values for max depth? So I could even say for depth in range, we can say 1 to 10. So we're going to try 10 different decision trees that each have a different depth. And so we can indent all of this. And then for our score, we can just keep track of scores right here. And actually, why don't we say depths is equal to that range. So we're going to try 10 different depths. And so now the important thing is instead of just saying 2 right here, we're going to say depth. So on the first round of this loop, we'll make a tree with depth 1. And on the second round of this loop, we'll make a tree with depth 2. And on the third round, we'll make a tree with depth 3, and so on and so forth. And what we can do is when we get our score, we can just append our score to our list of scores so we can visualize it later. And this is going to give us an issue. List object has no attribute scores. Oh yeah, we just want to say append. Boom. Okay, so now we should be able to. We now have a list of tree depths and how well they performed, right? So we could say plt plot depths and scores. And so on our x-axis, we can say depth of tree, and then on our y-axis, we can say f-score, and we'll even give ourselves a title saying, is a bigger tree always better? Look at that, being cheeky. Whoa, okay, very fun, very fun. So we get kind of a funky graph. And because that ran relatively quickly, I want to actually, let's see 1 to 20. There's also, if we were being really scientific about this, we would actually shuffle our data in between each loop. And so we would try it, we try it 3 times with one shuffle of data, or we try it once with a small tree, and then with that same tree, but shuffling the data to sort of average things out. But, okay, cool. So it's a little bit noisy, but it looks like, at least with a single tree, we don't get much better by making it much deeper than, what is this, like 2? So really, actually, a depth of 2 seems to be pretty good. And what that means is that after asking 2 questions in a row, it's going to ask questions that are too specific, and they won't actually generalize. So that's kind of a fun graph. Yeah, which I guess if we wanted to, I think doing the big sciencey thing of running it several times and averaging is probably more than we actually want to do. Cool. So we have tried a nonlinear model, and we got a better score. And this is, I guess, a good sign that there really are some of these nonlinear relationships, right? There are some things that it's like, well, if this thing is true, maybe that's true. But it's not just always sort of a linear relationship. But so how can we improve upon this? Well, I actually, now that I've shaken things up, I don't actually know if this will be an improvement, but it's something else that I want to try. And this is something called ensembling. So what we basically learned is that let's see, with this one. Okay, yeah. So in our decision tree, the decision tree that did really well here, 2 of its questions were about distance from home, and only one of them was about distance from last transaction. And one way we could think about this is that our single tree here kind of became an expert in distance from home, right? It learned a lot about distance from home and found just the right places to ask questions about it to get the best predictions, right? Skull Crusher for Life asks, wait, was that showing the depth of the tree was increasing the accuracy, or was it getting worse as the graph goes lower? Yes, this is a great question. And technically, it was showing it gets worse as the graph goes lower. So if you look technically from going, and you have to kind of zoom in to see this, technically from asking a single question to asking 2 questions, it did better. But then afterwards, it ended up doing worse. Which actually, an important point here is that this is on data that this tree has never seen before. If we actually, instead of testing on our test DF, and we actually tested on our train DF, so here, just for the time being, I will, I'm going to comment these out. Oh, come on. So here, we're training on our validation train data, and then we're testing on our validation test data, right? But what if we tested on the same data that we trained on? How would that change things? And my prediction is that actually, if you're testing on the data that you've seen before, that a big tree actually should be better. Yeah, there we go. So if it's just getting tested on the data it's already seen before, then a bigger tree really is always better, because it's kind of like it can just, if it's big enough, it can just remember specific things about every individual transaction, right? It can kind of memorize the answers. But it's only when we test it on data that it hasn't seen before that you realize actually adding all of that depth wasn't actually making it that much better, and that a relatively small tree was actually really good. A tree of just 1 or 2 was getting us a better score. It also is a sign that it's like, well, maybe it's not learning that much, right? If the best tree is only too big, then maybe it's not learning that much. And one of the reasons here is that decision trees tend to focus on one sort of thing, right? So here we noticed that we're really focusing on distance from home, because 2 of our 3 questions our about distance from home. And so one way that we can try to power up this model is by sort of chaining a bunch of them together. So there's this idea called random forests. Polar Void said, a forest thingy. Yes. And a random forest is basically saying, well, hey, what if we randomly created several decision trees and then we had them all vote on the right answer? So the way that we create a random forest is we import random forest classifier, and then we pass in a few things in there. I don't think we actually need the criterion. I think it defaults to Genie. But so first we say, how many trees should there be? And so for our forest, let's say there's 10 trees. Then we can say the max depth, and sure, let's say 3, or even actually looking up here, it looked like 2 actually did pretty well. So what if we say max depth is, we'll say max depth is 3 for fun. And then the final thing we're going to do is we could say here class weight equals balanced, but we can also actually specify specific weights. So in this weighting, I'm saying that I want you to care more about fraud, like 100 to 1, right? I want you to care about fraud 100 times more than you care about not fraud. So this is a little dictionary that says the weight for fraud is 100 and the weight for not fraud is only 1. So now, if we train this and test this, I mean, let's see what we get. Okay, 0.32. We are moving up in the world. That's looking a little bit better. And at this point, we could submit this, right? But why don't we've got some time. What if we did a little bit of science here as well? What if we said, yeah, let's do our same little loop. So what if instead of testing how deep our tree should be, we could test how many trees should be in our forest? So we can say or actually let's say forest sizes. And let's just pick a couple. We'll say 1, 10, 20, 30, 40, 50. I know I could do a range here, but I just want a list of numbers, gosh dang it. So we can say for forest size, in forest sizes, we can create a random forest and then train it. We can also keep track of our scores. And then just like before, for each time we create this, we'll train a new random forest, then we'll make predictions and score them, and add our scores to our list of scores. Cool. And so now let's scroll back up, and we can just copy this graph again. And, oh wait, that's not what we want, right here. And so here we can say, is a bigger forest always bigger? And we can say, instead of depth of tree, we can say numbers of trees. And we can plot our forest sizes and our depths. And, oh, let's see, are we still, yes, we're still testing the test. And there you go. Okay, this is interesting, and it seems compelling. And so now I actually want to increase this. So let's actually say, let's say range 10 to 200. And this might take a second to run. Aw, Darwin, bud. See, this is exciting. I'm all about the drama this Global Hack Week. We got the pupper to just, give us some barks occasionally. Let's see. Nalarepus asked, am I wrong to assume random forests are supposed to be based on arbitrary weights? Yeah, so they are, randomly initialized. So they do all learn something, but they are all given a different set of features. So the randomness, this is actually a great question. The randomness comes from the idea that, that at each step, they are given a different set of features to look at to decide what question to ask. But yeah, that's a great question. So the weights are not totally random, but they are but they are random in a sense because the results are not random, but the questions they ask end up being a little bit random. Okay, so now we've really tested this. Is more trees always better? And oh, it's still running. Okay, so I guess, yeah, once you get, oh, actually, I know what's wrong with this. We should have used a step. Just do every 10. Because when you get up to the, in fact, actually, because I want to know how fast this is going. Okay, cool. So this is actually pretty fun. You can see as our forest gets bigger, it takes longer to train each subsequent forest. Those first were just flying by. And now, oh yeah, to train 180 trees, it takes, almost a second, right? Okay, cool. So now we should be able to graph this. Whoa, that's interesting. I guess we started just going up to like 20, didn't we? Why is 25 so bad? Interesting. Okay, actually, do we have time? Okay, I'm going to put a pin in this because I want to come back to this question of trying to find the correct size of forest, because I think this is actually really interesting. So we're going to actually pick this back up tomorrow and do a little more science and see if we can figure out the right number of trees in our forest. And we will also look at the sort of the elephant in the room of other nonlinear models, and we will probably do a neural network, because it wouldn't be Global Hack Week machine learning if we didn't do a neural network, right? Good deal. Yeah, I think we'll leave it there. But this was good enough that why don't we submit this? We have our random forest that's doing pretty good, and let's see how that does on a submission. Which, if you're following along, you should submit too. I will say one thing that is traditionally really desirable about random forests is that you can keep making them bigger and bigger, and they might not keep getting better, but they won't get worse, right? They won't do like up here with a single tree getting deeper. It just kind of fell off a cliff, right? Our performance actually decreased as we made our model bigger. But here you at least know that your model isn't going to get worse just for adding more to it, right? We're still hovering around, 0.32. Which notably, actually, we now have like this submission will probably take a while because it has to go and train all of those random forests in our loop. Running for, okay, we submitted. Let's check the, let's see, the leaderboard. And okay, 0.32, which interestingly, this is you're getting one little sneak peek here because I'm not gonna make it so you can't see the score. But so the score on the public data is 0.32. The score on the private data is 0.28. So it is a little bit worse on the private data. Now you don't know what your private score will be at any given time, but you know that if you make this exact submission, you might make somewhere around 0.28 on the private score. But hey, I see a lot of scores getting up there. Oh, Trisha has submitted. Derek and Jordan, great. And Kaga Prague asked, please share part 4. Yes, absolutely. Absolutely. Did I not make it public? Let's see. Okay, it should be public, and I will copy that link and paste it. And it should be, at this point, if we go to code, okay, there we go. So it shows up as part 4 down here. Yeah, you are very welcome. Yeah, folks are fast. This is I've learned doing some of the Kaggle featured competitions. I wrote a little bit of starter code to help people out, and within I swear 15 seconds after posting, someone had pointed out one. It wasn't technically a bug, but it was this open issue with NumPy, and we had a conversation about it. But it was wow, the one sort of interesting little catch thing, someone caught it within 15 seconds. So yeah, Kagglers are fast. You could be fast. You could be a fast Kaggler. Well, good deal. I guess I will hang out for a few more minutes and see if we have any questions. Otherwise, I will drop the check-in form one more time. So go and get credit for being here. And I guess we'll do one more reiteration that you can win a swag drop either by coming in first or second place. So Derek and Jordan are doing okay, but you could actually be, if you just submitted that thing that we just dropped, the Random Forest submission, you could have a score that's second place right now. Now, obviously, everyone will do that, and so it'll blow up. But also, by being anywhere on our submission leaderboard, you have a chance to win the raffle and get a swag drop. And then the other two ways are to either post some code. So I will go and look at all the code posted, and I will give ConquerProg a thumbs up because I haven't looked at it, but I'm sure it's great. And you get a thumbs up just for being the first person. Or starting a discussion. So this could be a comment on a notebook, or you can formally start a discussion. Alvin posted a discussion saying Darwin is adorable. Incredible. Thank you. Thank you. I can spell, I promise. I couldn't agree more. We'll give a little happy face. Oh, the happy face looks bad. Boom. So right now, if no one else posts a comment, Alvin / Polar Void is going to win for the discussion, and ConquerProg is going to win for the data analysis. All right, I think we were for publishing code. I think on that note, we are going to call it there. The one last thing I will point out is that we technically have 3 more days, so I think this should end on Friday. And so even after our last submission, there's still some more time for you to work and try things out and try to get a higher score. And I would totally recommend that you keep hustling, and then I'll pop onto Discord and announce all the winners probably Saturday. If you are looking for this later, you can go on to Twitch and you can look at all videos. And I think it's saved on Twitch for 7 days. It might be 30 days. You can also find this on YouTube where it is saved forever. YouTube for the win. Alrighty. Well, in that case, if we don't have any other questions, oh my goodness, y'all, 49 entries. We're getting up there. I love this. If we don't have any other questions, I am going to play us off with Kalimba and call it a night. Thank you, friends. Happy Tuesday and happy hacking. I tune it never, Alvin. I tune it never. And Trisha, thank you so much. I'm so glad that you're able to make it. It was great to have you here. Thomas, thank you for being here. Thank you, Skull Crusher. And I'll see you all tomorrow. Good luck and have fun.